Ayan. So once again, good afternoon to everyone. So I hope that you've had a great lunch. So please check the chat box na lang for our attendance for today. So in the meantime, while you fill up our attendance form, so let me go over our target outcomes for this particular session. So in this session, we are now starting with a new module, namely our chemical kinetics. Now, our last module, the chemical thermodynamics, dealt with the energy changes that accompany physical and chemical processes. This time, we're now talking about the chemical kinetics, which in turn deals with how fast or how slow a reaction is. So in chemical thermodynamics, we were able to learn how to compute how much energy is involved in a particular process. We also learned whether a particular process is spontaneous or not. But another thing that we also might be interested to learn, especially when we're dealing with chemical reactions on an industrial scale, is whether a given reaction will proceed fast or will it proceed slow? And what can we do to make it proceed a little bit faster? So that is the point of our chemical kinetics. So with this module, we start off with the kinetic molecular theory, going on to the collision theory, and then our reaction rate. So for today's session, we aim to be able to achieve the following target outcomes. So by the end of this learning guide module, the students should be able to 1. Apply the collision theory to describe a chemical reaction. 2. Relate the collision theory to KMT. So we abbreviate kinetic molecular theory to KMT so that we don't have to pronounce all of that since it's a bit of a mouthful. Number 3, we have to be able to relate the nature and concentration of reactants to the rate of reaction. And finally, number 4, explain the effect of nature and concentration of reactants using the collision theory. So with that, we are now ready to start. So we start off with our kinetic molecular theory, or KMT for short. So the KMT explains to us the states of matter and supposes that matter is composed of tiny particles that are always in motion. So whether you have a solid, a liquid, or a gas, we can just visualize that particular substance as being composed of tiny particles that are always constantly in motion. However, ang KMT natin is best able to describe our gases, in particular, the ideal gas. Now, the ideal gas, as the name implies, it's a theoretical construct. In reality, we don't really encounter ideal gases. So real gases have behaviors that differ from the ideal gas. However, the idea ng ideal gas is useful for us to just have a very simple model as to how our real gases work. So even if it is not really something that we see in our day-to-day experience, the ideal gas still gives us very good insights as to the behavior of our gases we encounter in day-to-day life. So an ideal gas, you might have already encountered this one in our Chem 1. So for the purpose of this discussion, an ideal gas is just any imaginary gas whose behavior perfectly fits all the assumptions of the KMT. Again, it's imaginary because in real life, our real gases do not always follow all of the assumptions ng KMT natin. There will be a little bit of deviation here and there, particularly if you have gas at a very high pressure or at a very high temperature. So the assumptions might change. Very low temperature rather. So that's our KMT. So it helps us be able to really understand the behavior of our gases in particular. So our KMT, so it is underpinned by 5 particular na assumptions or postulates. So these assumptions are as follows. So first, according to the KMT, our gases are made up of very large numbers of tiny spherical particles that are very far apart from one another as compared to their size. So you can imagine, let's say you have a sample of gas and you can actually try to compare it to, like, let's say the room that you are in. So let's say that our sample of gas is contained within a container, which we now visualize as the room that we are in right now. Now our gas, let's also visualize this one as a thought experiment as being kind of like a marble. So if you try to compare the sizes of the room, the container in which the gas is held, and the gas molecules themselves, so there's no question. Our gas molecules are so very small compared to the size of our room itself. So basically, our gases in the gas sample where they are being contained, you basically don't encounter so very much of it. So most of the volume of a gas sample that we have is just comprised of the empty space between the particles. Really, it's because the particles are so small that they really don't compare to the size of the container that they are in. And likewise, our gas particles are also much, much greater in distance from one another compared to the particles that are found in the liquid or the solid. So this one is particularly important because since our gas molecules are very far apart, it allows our gas particles to move constantly in a rapid motion in random directions. So if you compare it to something like the particles in a liquid or a solid, so the particles in our solids or liquids, they are found a little bit closer together. So as a result, so they are not as free to be able to move around. So postulate number 3, particles are able to move in straight line paths. So you don't expect them to be moving in circular paths or curved paths at all. And whenever you have two gas particles meeting each other, so they will be able to collide. Now the collision between the gas particles and between the particles and the container walls are elastic collisions. So you have in here a GIF that I have in this PowerPoint. So you have in here a dog playing billiards. So an elastic collision, we can visualize it as something like the collision of our cue ball to our billiard balls in here. So as you can see, our cue ball can just bounce off our other balls or the sides ng ating pool table, or like in this case, so let's just wait for that one here. So in here, it might be able to strike another ball and it will come to a complete stop. So that is how we can try to see elastic collisions in our day-to-day life. So an elastic collision technically is defined as a collision in which there is no overall loss of kinetic energy. Kung mag-stop man ang ating cue ball like in here, so its kinetic energy has been completely transferred to the other ball. So that basically, the sum of all their kinetic energies ng ating balls that are colliding will always remain constant, no matter what happens. So kinetic energy may be transferred from one particle to another during an elastic collision, but there is no change in the total energy of the colliding particles. So that is our elastic collision. So the same is true if our gas particles don't collide with other particles, but rather with the container that it is inside. So it's still going to be an elastic collision. So the kinetic energy na ating gas particles are going to be transferred into the container it is in. So that is what gives rise to the pressure that our container experiences from the gas that it contains. So number 4, the fourth postulate of the kinetic molecular theory is that there is no attractive or repulsive forces between the gas particles. So this is important because, as you can imagine, if our gas particles move very close together, like when they collide in here sa ating GIF, so if there's any attractive force between them, so the two balls in here sa ating GIF, they might stick to one another. Now, as you have more and more of the balls that are going to collide with the two balls that have already stuck together, you can imagine na parang nagka-clump na sila together. And that will lead to the formation of a condensed state, either a liquid or a solid. So we assume that there is no such attractive force going on. So whenever a gas particle collides with another gas particle, they are not attracted whatsoever to each other, so that there will now be, they will always remain gases lang naman. So the opposite is true as well. So our gas particles also do not exert any repulsive forces towards each other. So that is our fourth postulate. And finally, and probably the most important one amongst here for the purpose of our discussion is the fifth one. So the average kinetic energy of gas particles is dependent upon the temperature of the gas. So let me throw it over to you muna at this point. So let me ask you, let's say you have a cup of coffee, let's say, and you want to know ano ba ang temperature ng ating cup of coffee. So how would you, as a normal person, measure the temperature of our cup of coffee? So any ideas how we measure the temperature ng ating coffee? So feel free to raise your hand, speak up, or type lang sa chat box. Okay, so si Dash and said and Danielle says that they'll use a thermometer. Any other ways that we can try to be able to measure the temperature ng ating coffee? So any ideas how we go about doing that one? Okay, so if let's say you don't have a thermometer at home, so Inia says that we can just simply touch it and we already have an idea whether our particular cup of coffee is gonna be hot or cold. So that's another way that we can measure the temperature. So Jiro is a little bit fancy. He says na he has a heat scanner. So pahiram naman nan one of these days. So ayan. So in our day-to-day experience, so we have ways to be able to measure the temperature, either by using a thermometer or just by using our senses, or maybe some other type of device. However, if you go down to the molecular level, so obviously we don't have a thermometer na kasing laki lang naman ng gas particles. So really, we need to be able to come up with a definition of temperature on a molecular level. Since basically we don't have any way of measuring temperature at such very small na scale. So by the way, we have this one. So you have in here an animation of our gas particles as they move along in a container. So they are moving very, very fast. They are just slowed down in this GIF. My clock ka sa baba, it says here that this is 35,000 fs or femtosecond. So 1 femtosecond, so just so we can understand just how fast our gas particles are moving, 1 femtosecond is 10 raised to the negative 15 second. To put that into context, every time that we blink our eyes, so that lasts 0.3 second. Or, expressing that one in femtosecond, that is, I don't know how to read this number. It's just a 3 and followed by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 zeros. So that's a lot of zeros. So basically, a blink of an eye is almost an eternity in terms of the motion ng ating gas particles. So some things we can observe here. If you look at this one, so hanap tayo na medyo slow moving. Saan bang slow moving dito? Let's find a slow moving particle. So you can have something like, let's say this one. Ito siya. So it's moving a little bit slow. And there are other gas particles in here that are moving quite fast compared to the one that we highlighted earlier. Let's say, let's look at this one over here. So it's moving a little bit faster. So at a given temperature, our gas particles can have a variety of speeds. Some of them might be moving quite slow, while some of them are moving very, very fast. So what we can do now is we can just try to be able to measure how much of the gas particles are moving at a particular speed and be able to construct a graph for that. So that graph is what we call as the Boltzmann distribution. So let me start the animation for this one. 300 trillion according to Howard, yung ating femtosecond. I can never remember. I think lumampas na siya ng trillion, but I'm not sure. I can never remember very large numbers. Scientific notation lang talaga ako hanggan. So let me start the animation for this one. Since this one was animated for us to be able to better understand what's going on. Okay, that's done. So we have the Boltzmann distribution. So in this Boltzmann distribution, we can just draw an X and Y axis. On the Y axis, we now plot the fraction of gas particles that we have. Starting off at the bottom at 0, so let me use the pointer here. So starting from 0 at the very bottom, and as you go up our y-axis, so the fraction of particles gets larger and larger. Similarly, on the x-axis, we can now plot the molecular speeds. So starting from the leftmost side, as we go further on to the right, you can see na ang molecular speeds natin are increasing. So what we can do, we can just take a sample of gas particles and try to be able to observe the speeds of our particles at any given temperature. So at, let's say, 100 Kelvin, we now get the following graph. So like in the animation we had earlier, so we expect that there would be some of the gas particles that are moving very slowly, just a small fraction, but in any case, they are still there. So since there aren't very many of them who are moving very slow, na almost close to zero na, so medyo mababa lang ito, ang height ng point na I'm pointing on the laser pointer. Likewise, there are also some gas particles, not a lot of them, but there are still some who are moving at very high speeds. So there are some na we can see are moving at mga around 750 meters per second. So it's a very small fraction lang ng ating total, but there is still some. So it is located here sa ating graph. So as you can see, there is a large collection of possible molecular speeds from 0 to almost 1,000. However, ang vast majority ng ating gas particles at 100 Kelvin, they are represented by the peak ng ating curve, as shown in here. So at the peak ng ating curve at 100 Kelvin, we can just draw a straight line from the peak going down into the x-axis. And we can now measure the molecular speed, the most probable molecular speed for our collection of gas. Most probable because ang karamihan sa kanila has that particular na speed. So the most probable speed for the majority of the gas particles is over here on the x-axis. So if I get a ruler for this one and measure the distance from here to the 0 divided by 0 distance to the 500, I would estimate this one to be around 300. So the vast majority of our gas particles have a most probable speed of around 300 meters per second. Now we can take that same gas particles in our sample and raise the temperature from 100 Kelvin. Let's say we now have at 300 Kelvin. So kanina, again, we had 300 meters per second as the most probable molecular speed for the majority of the gas. However, ngayon, as you can see, ang peak ng ating curve is nagbago. Okay? So again, going from the peak of our curve and drawing a straight line downward to this one, we can see na ang most probable molecular speed here is around 500 meters per second na when the temperature is 300 Kelvin. Again, it doesn't mean to say na tumaas ang ating most probable speed na there is no longer any gas particle that is moving quite slow. There is still some that are moving very slow. So just a small fraction, that's why medyo mababa ang height nito ng point that I'm pointing here right now. And there are also some in here that are moving very fast, much faster than the most probable speed. So there are a lot of them. That's why medyo mababa lang ang height for this one. But then again, the majority of our gas particles at 300 Kelvin is represented by the peak here. So they are moving at a most probable speed na 500. So moving forward, we can heat it up some more to 600 Kelvin. Look at the peak of this one, or maybe later lang. And we can further heat it up to 1000 Kelvin. So this one here is our Boltzmann distribution. So take note, each curve here represents just one sample. So same sample lang siya for each curve. Ang difference lang is we just raise the temperature from 100 to 1000. So in the case of our 600 Kelvin, again, we can just point or rather draw a line from the peak going down to the x-axis. And using a ruler, we can measure this distance from 500 to this line over here, the dotted line, divided by the distance between 500 and 1000. And from that, I can already infer na the most probable speed at 600 Kelvin is 785 meters per second. So that most probable speed is the most probable speed ng majority ng molecules. since that is the one having the greatest fraction of particles. We can read the fraction by making a line na horizontal and pointing it to the y-axis. And similarly, for our 1000 Kelvin, we can just draw a line going down from its peak, right over here, to the x-axis, and we find that its most probable speed is 984 meters per second. So from this Boltzmann distribution, for our particular sample of gas, we now are able to arrive at the following conclusions regarding the behavior of our gas. Okay? So first na obvious conclusion here. So we see that as the temperature increases, the most probable speed of the gas molecules increase. Galing ng 600 Kelvin, which has a molecular speed, most probable speed of 785, the most probable speed increases to 984 when we have a temperature of 1000 Kelvin. So that is a trend that we observe regarding our Boltzmann distribution. Okay. So also, I'd like to ask as well from you guys, so can you see any other trends as we increase the temperature, maliban sa ating most probable speed? Okay, I can't, oh well. So I can't read the chat box, so maybe just feel free to turn on your mics and just tell me, is there any other trend that you observe when we increase the temperature para sa ating graphs? So just please turn on your mic since I can't read at the moment the Google Meet na chat box. Since I have the entire screen being displayed. So any trends that you observe, going from 100 to 300 to 600 to 1000 Kelvin. So anything that you observe regarding our graphs. So again, I can't read that chat box, so just please turn on your mic if you have an input.
Wala ako maisip, sir.
Okay. How about the shape? So yun, let me give you a hint. So is there anything about the shapes that you can see na nagbago when we raise the temperature?
Sir,
Yes, please go ahead.
nagiging flat po yung, sir, yung graph habang ga-increase ang temperature.
Ayun, okay. So can you please state your name? Sorry, hindi ko lang mabasa ang chat box kasi. So I don't know who's speaking. So can I please have the name of the person who answered just now?
Ang bulod to po.
Okay. Okay, so thank you so much for that observation. So as you can see, ang 100 Kelvin natin, it's already quite steep at the beginning. So you can imagine this as kind of like a mountain. So the 100 Kelvin curve, para siyang mountain na sobrang matirik. Now as you go higher and higher in temperature, ang mountain natin nagiging less steeper so that from the 100 Kelvin na, parang almost vertical na siya na bundok that we need to climb up just to go to the top. As we go down higher and higher in temperature, ang ating mountain now becomes something that we can more easily walk on. So another trend that we can see is that our distribution flattens at higher temperatures. So that's also another na observation that we have. And finally, we can look at this one. So let's just focus on the 600 and the 1000 Kelvin here. So if we look at the proportion ng ating particles having a speed of 1,500 or greater, so ito siya ang blue na area that we have in here. And similarly, for the 1000 Kelvin, so the proportion of gas molecules at 1000 Kelvin having a speed of 1,500 or greater, that's represented by the red curve over here. Natabunan na siya ng kaunti by the blue area that we have. So if you try to compare how big the blue area is to our red area, so our red area is larger than the blue area. So what this means to say to us is that as we increase the temperature, there is now a larger proportion of the gas that's now able to move at higher and higher speeds, even greater than our most probable speed. So that is our trend for the temperature according to the Boltzmann distribution. So this allows us now to be able to define temperature at a molecular level. So we can now say na to be able to measure the temperature, all we need to do is just to be able to measure the speeds of our gas particles. Now the speeds of the gas particles, so you might be familiar with this formula from physics. The speed of the particles is related to the kinetic energy that the gas particles possess, according to this equation right over here. So the higher is the speed, definitely the greater is the kinetic energy. So basically, at a molecular level, our temperature simply is a measure of the kinetic energy our molecules are possessing. So that is the actual na idea that is under kay postulate number 5. So that explains its idea in the number 5 postulate. That the average kinetic energy of gas particles is dependent upon the temperature of the gas. Since the kinetic energy is related to the speed, and as we saw, habang tumataas ang temperature, tumataas ang speed, so the kinetic energy is directly related to the temperature of that gas. So that is our Boltzmann distribution. So now that we have our KMT to help us better understand the behavior of our gas, we can now try to use the KMT to explain how a reaction occurs. So a reaction occurs and it is being described by our collision theory. So very simply, the collision theory tells us that for a reaction to occur, the reactant molecules must collide with an energy that is greater than some minimum value and with the proper orientation. So as a way for us to better visualize this one, so let's consider this reaction of carbon monoxide gas with oxygen gas. So I think I haven't yet edited out the mistake in here. Let me just edit muna very quickly. So the reaction of carbon monoxide gas with oxygen gas produces carbon dioxide plus an oxygen atom, like so. So let's say we have the following na reactant molecules to start off with. So meron tayong carbon monoxide. Ito siya, right over here. So let me use the pointer again. So this is the carbon monoxide molecule. And you have the O2 molecule right over here. Another CO molecule and another oxygen molecule right over here. Now let's say that we try to observe them colliding with one another. So let's look at this one, itong may yellow arrow here sa taas. So notice here na itong ating dalawang reactant molecules, they are not properly oriented. So first off, itong oxygen natin, it is colliding with the CO at an angle. And furthermore, itong oxygen atom ng O2, hindi siya nag-collide to the carbon atom of our CO. So as a result, so since it's not properly oriented, so no reaction has occurred. If you have billiard balls as a way to visualize this, so you can just imagine two billiard balls bouncing off one another. So nothing has occurred except for that one. So since no product has formed after these two have collided, we now have what we call as an ineffective collision. Since no product was formed from this particular na instance. Now at this point, so we're done with these two na pair here sa taas. Let's look at the second pair here sa bottom. So as you can see in here, so this one seems to be more properly oriented. So first off, ang oxygen natin and carbon monoxide, so they are colliding with each other head to head. And furthermore, ang oxygen atom na ito is colliding with the carbon atom ng ating CO. So as a result, if we focus on just these two, we observe na something actually occurs. And finally, our product na CO2 was able to form. So this one, since a product has formed, this is an example of an effective collision. So an effective collision happens when chemical bonds are broken. Yung oxygen from the O2 kanina, its bond is broken down, and the oxygen from the O2 bonds with the carbon atom, producing our product. So that is what's happening in an effective collision. So it only happens in this case since the two reactant molecules are properly oriented and our oxygen atom is colliding with the atom na kailangan niyang magkaroon ng bond with to make the product. That is our effective and ineffective na collisions. So it's via collisions that we can be able to produce our products starting from our reactant molecules. So that takes care of the second statement here. So sabi ng collision theory, kailangan daw with proper orientation for a reaction to occur. So let's now try to look at the first statement here. So a reaction only occurs when the molecules collide with an energy greater than some minimum value. So let's look at this first na part ng ating statement ng collision theory. So here we have the activation energy. So it is defined as the minimum energy of collision required for two molecules to react with one another. So the activation energy, its symbol is E sub A. And we can visualize it using an energy diagram. So here you have an energy diagram. On the y-axis, you have potential energy. Starting with the 0 dito sa baba. And going up, we have higher potential energy. On the y-axis, you have the reaction progress. starting here at the very left, so no reaction has occurred yet. And as we go further and further to the right, so the reaction progresses so that from reactant, magkakaroon na tayo ng product. So let's say we have our reactants having a potential energy right over here. So as the reaction progresses, so we're now able to form this particular na curve in the energy diagram. So notice here, so before we can go to the reactants, to the products, so we have something like a bump or a hill na kailangan nating akyatin before we can get into the products. So the difference in potential energy ng reactants and the products, so actually that represents our delta H, which in this case is less than 0, since mas mababa si products in potential energy compared to the reactants. While this hill over here, in our energy diagram, this represents now our activation energy. So by the way, this is an exothermic reaction since delta H is less than 0. So we can actually visualize our activation energy as kind of like a barrier that our reactant molecules have to climb over before they can be turned into products. We can make the same and a similar energy diagram for an endothermic reaction as follows. So as you can see here, ang delta H natin is greater than 0 since ang products has a higher potential energy than the reactants. And this hill na kailangan nating akyatin to get into the products, this represents our activation energy. So actually, we can envision the activation energy as just that. It's kind of like a barrier or like a hill or some obstacle course na kailangan natin na i-overcome to get from one side of this obstacle to the other side of the obstacle. So you can imagine if you're the climber in this picture, so maybe you haven't had lunch that day, so you don't have as much energy. So hindi mo kayang akyatin ang ating hill over here or the obstacle. Well, if you had a very good lunch, so you're probably better able to climb up the obstacle and reach the product na side. So just on the other side of our obstacle course. So how does our activation energy going to affect our reaction? So we have this particular animation over here. Okay, so let me break it down to you. So start off tayo sa mababang temperature muna. As you can see, medyo mabagal ang pag-collide ng ating dalawang reactant molecules at low temperature. So since they're not moving so very quickly, they are not very energetic at all. And as such, since the reactant molecules are not energetic enough, so basically they don't have enough energy na kaya nilang akyatin si activation energy barrier. So basically, no reaction has occurred. They basically just bounced off one another. In contrast, if we increase the temperature, we observe na this time our gas molecules are able to move much faster. So in this case, our gas molecules have moved faster, and as a result, they now possess enough kinetic energy na they're able to overcome the E sub A or the activation energy. Actually, na medyo exaggerated itong ating diagram. So lumampas na siya ng sobra-sobra from the activation energy. So it has enough energy to overcome the hill. And as a result, so a reaction is occurring. And we now form our CO2 pa rin and the O as our other products. So that is how the activation energy serves to be able to hinder the reaction from happening. So any gas molecule, like in here sa taas, which do not possess enough kinetic energy, so they're not able to form our products. Whereas these ones over here sa baba, with a greater na with a greater amount of kinetic energy in them, so they are more able to overcome the activation energy barrier. And that is why they are able to form the products in this one. So all of that leads us to the rate constant. Now the rate constant, so it is simply a way for us to quantify just how fast or how slow a reaction is occurring. So the rate constant, we symbolize it by the small letter k. So it is given as a product of three factors according to our collision theory. By the way, the rate constant, so the smaller is the value of this one. So smaller k, mas mabagal ang reaction from occurring. The larger is the k, definitely the faster our reaction is progressing. So our k is given by three factors. So one, that is our z, the frequency of collision. So definitely the more collisions are occurring, and therefore, mas mabilis na nako-convert si reactants into products. The small letter f, that is the fraction of collisions having enough energy to overcome the activation energy. And our p, which represents the fraction of collisions that have the proper na orientation for a reaction to occur. So multiplying the z, f, and p together, we now get the value of the rate constant. So assuming that our reaction has a lot of molecules energetic enough to overcome the activation energy, and they are all colliding at great numbers, then the third factor is the orientation ng molecules natin. So this is a very quick review lang ng kanina. So in here, no reaction occurs since head-on nga sila, but this case, the oxygen atom is not colliding with the carbon atom. While in this example, a reaction occurs because you have a carbon, the black one, properly colliding with the oxygen atom ng O2, so that they're able to form the products. So the orientation of the gas molecules or reactant molecules is very important. So there are a couple of factors now that influence our rate constant. One of these factors is the nature of the reactants themselves. So if you have different metals, let's say, and we try to react them with an acid, so the reaction might have different speeds depending on the reactivity ng metals. So we have this list on the left, which allows us to compare the reactivity of different metals and nonmetals. We call this list over here as the activity series. Okay? So starting off with the pinaka-top in here, you have potassium. Potassium is a highly reactive substance. So it's so reactive that it can react with water alone, or even with the moisture in our air. So this reaction will occur very fast and very violently. Sodium is also similar, so it can react with water as well. Compare it to something like, let's say, dito sa gitna, let's have iron. So our iron by itself does not react with water, but it does react with acids. And further on down the line, So we have hydrogen just for comparison's sake. We have something like our silver, gold, and platinum. So silver, gold, and platinum at the very bottom ng list. So these are highly unreactive na metals. So if you have your gold jewelry, for instance, and it is exposed to the acid in, like, let's say, our sweat, so it doesn't react at all. So it just remains in very good condition. In fact, we can see a lot of gold coins and silver coins from hundreds or thousands of years ago buried under the ground where it is exposed to the acidic conditions in the ground, and it still remains in pretty good shape even after having been buried 100 or 1,000 years ago. So it is because the silver and the gold are highly unreactive na metals according to our activity series. So the activity series tells us that the topmost elements are the most reactive and that metal reactivity decreases as you move down the series. So for instance, if we compare lithium and our potassium, so since lithium it's a little further down along, so lithium is less reactive than the potassium. So potassium is the most reactive out of all of them. So as a bit of an application for this one, so you have our highly unreactive metals like mercury, silver, and gold. So they are actually quite useful in dentistry. For instance, our more modern na mga postizo or tooth replacements, for instance, are made up of a mercury alloy. But they have since been replaced by some other na less toxic na metals. In ancient times, you have also some replacement teeth which are made up of gold. So gold is quite good, as you can see, since it's highly unreactive lang naman. Of course, assuming na may pera ka para makapagawa ng gold na replacement tooth. So gold is suitable for dentistry because also it is malleable, so it can be easily shaped in the shape of our tooth. It's immune to corrosion, so even if it is exposed to our saliva and to the acids in the food that we eat, so it will not be corroded or destroyed at all. And it closely mimics the hardness of natural teeth. So you can see a lot of these in older na mga, in ancient peoples. So the gold tooth is quite a bit common with them. Now, of course, it's a little bit more out of reach para sa atin ngayon since the gold is already very expensive. But we can still see why they went to the gold to make their substitute teeth. So it's because our gold is a highly unreactive na metal. Now, aside from the nature ng ating reactants, guys, another way that our speed of reaction is going to be affected is via the concentration. So we have an experiment for this one, guys. So it's just a picture lang naman, or rather it's a video experiment, but we'll just leave it for the next meeting since we don't have much time remaining. So another factor affecting the rate of reaction is the concentration. So the main takeaway for that one is that when we increase the concentration of our reactants, the rate of the reaction also increases. By the way, the rate, in terms of mathematics, rate is synonymous to the speed. So the greater the concentration is, the greater is the speed of the reaction. So that's what this sentence here is trying to tell us. So in summary, we have the following. So for today, we learned about the collision theory. So it states that two molecules react after colliding only when the energy of collision is greater than the activation energy. and when the molecules are properly oriented. So the nature of reactants will affect the rate of reaction according to the activity series, since there are some substances that are more reactive than others. And finally, increasing the concentration of reactants increases the rate of reaction. So that basically sums up our KMT, our collision theory, and some factors that affect our reaction rate. So at this point, let me turn it over to you guys. So are there any questions or clarifications you'd like to raise regarding our lesson today? So Phileas has a question. So mag-increase, not a question, but an observation pala sa ating Boltzmann distribution. So mag-increase din yung number of possible speeds. So that's also correct, Phileas. So kung babalik tayo sa ating Boltzmann distribution, sa 100 Kelvin, limited lang tayo from 0 to 1,000. Whereas, at the 1,000 Kelvin, so we have a greater number of speeds na possible. From 0 meters per second, pwede tayo lumampas until mga almost 3,000 meters per second. So that's also a very good observation on the side ni Phileas. So job well done. So any questions you'd like to raise at this point so we can answer them?
Sir,
Yes, please, Jazz.
the formative assessment for LG 2.1 and 2.2, is that by next week po? In the
Yes.
Okay, thank you po, sir.
So you'd still have 1 week to be able to finish that one. Since we weren't able to meet earlier today. So definitely wala na kayong oras to do this. Any other question you'd like to raise? Thank you, Jazz, by the way.
None po sa akin, sir.
Okay, no questions from Zed. How about the others? Questions, concerns, or anything you'd like to raise?
None po, sir.
Sige. So, time check natin. It's now 2 o'clock. Thank you, Inya, as well. So, it's 2 o'clock. If you haven't yet done so, please be sure to answer our attendance form for today. So, I hope that you've learned something from this discussion. So, I'd like to thank you at this point for an active participation today. So, it's now 2 o'clock in Thursday. So, I hope you enjoy the rest of your week. Stay safe always, and until next time.
Thank you po, sir.
Thank you, sir.
Thank you, sir.
Thank you, everyone.
Bye, sir.
Thank you po.
Thank you. Stay safe always.